So we've got a battery, resistor, capacitor. They're wired together to form a complete loop. And let's assume that at the instant we hook everything together by flipping the switch, the capacitor is empty at that moment. But of course, it's immediately going to start filling up. If we write out the loop rule for this, or the loop rule equation for this circuit, what would the loop rule equation look like? What would we have to include in that?
Capacitor, resistor, battery is all equal to 0 when you add them up.
Right. The sum of the delta voltages for the entire loop, that has to add up to 0. And if we split that up into delta V for the battery plus delta V for the resistor plus delta V for the capacitor, those all have to add up to 0. And then we could fill in formulas for each of those. Battery is just going to be a constant plus epsilon. What's the usual delta V for a resistor?
Minus IR.
Yeah, we got a negative IR from Ohm's law. And what about for a capacitor? What is it?
Q over C, right?
What was that?
Q over C.
Yeah, Q over C. Q in the sense that, in the sense of charge, because the capacitor only has voltage in the first place because it stores charge. If it doesn't store any charge at the moment, such as at time 0, then it has no voltage. When it starts storing charge, it gets voltage that is pushed back proportional to how much charge is stored on it right now. And then C, the capacitance, is just a constant of proportionality here. More capacitance means it takes less voltage to store a certain amount of charge. Or to put it another way, delta V times C equals Q if you multiply both sides by capacitance. So lots of capacitance means you get a lot of charge stored even if you just have a low bit of voltage. Also, we generally write this as negative Q over C in the sense that the capacitor is pushing out against more charge coming into it. If you're trying to push more and more and more charge into the capacitor is pushing back against that. In this case, the capacitor would be pushing against the battery. But even if you have a capacitor discharging, even if you've just got a capacitor, resistor, and no battery in the loop, we would still treat delta V capacitor as negative Q over C because the push from the capacitor is attempting to remove charge from itself. It's trying to discharge. So the negative here essentially represents direction, that the push from the capacitor is pushing in the direction trying to decrease its own charge. So those formulas all have to add up to 0. And it's helpful in this case to rearrange the equation a bit by adding these terms to both sides. Get rid of the negatives. So we get epsilon equals I times R plus Q over C. And as I mentioned last time, you could interpret this as saying the battery can do two things. The battery can cause current to flow. The battery can cause charge to be stored. But it can't do lots of both. It can do lots of one and a little bit of the other. You can have lots of current when only a little bit of charge is stored. Or you can have lots of charge stored when there's only a little slow current flowing. Or you can have some of each. You can have some charge stored while there's some current flowing. But you can't have lots of each, and you can't have none of each. You can't have a situation where there's no charge stored in the capacitor and no current flowing, because those wouldn't add up to the voltage of the battery. The only way that would work is if the battery's voltage was 0. In other words, if there was no battery at all. But if there's a battery, the current and the charge, modified by these multipliers, have to add up to this same constant at all times. So more charge means less current, and vice versa. Any questions on that so far? And moreover, we can actually throw in the numbers here. We know epsilon is 12 volts. The current's going to be changing, so we should leave that as a variable. Resistance is 3 ohms. Charge is changing, so we should treat that as a variable. And then capacitance is 2 farads. So 12 equals I times 3 plus Q over 2. At any given time, the charge and current have to follow this pattern. So that's one equation describing how charge and current are related. How else are charge and current always related? What does current actually mean?
How much charge is flowing per second?
Right. So we can treat that as a derivative, a rate of change. Change in charge over change in time. How much charge flows past that point per second? So we could even write this in terms of derivatives. We could say 12 volts equals, or leaving off the units for a moment, just to focus on the numbers. 12 equals 3 times Q prime derivative plus 1/2 times Q. So what we get is what's called a differential equation, an equation that's describing the relationship between the function and its own derivative or differential. And there are various ways to solve this, but anytime you've got a situation where the function and its own derivative add up to 0 or add up to a constant, what type of function would you expect that to be?
Exponential?
Yeah, this is always going to lead to an exponential function. In any situation where you've just got a constant times the derivative plus a constant times the function equals a constant, or 0, which is a constant, then that always leads to an exponential function. And in this case, if we actually try writing that out, we know that charge is exponential. So we should be able to write it as an exponential function. Q of t equals, and how would you expect to write that out? If it's going to be an exponential function, what would you expect the equation itself to look like?
Would it be Q0 times e to the, I know there's gonna be time, but there'll be some sort of constant, I just don't know what.
Some constant times time. And also, would we expect this to be exponential growth or exponential decay? Is it approaching an asymptote, or is it just continuing to change faster and faster?
Well, if it starts at 0, the charge is gonna keep increasing until the plates can't like hold anymore.
Right, so we do approach some steady state asymptote. We should expect the graph to look like, if we're graphing time versus charge, we're assuming that we start off with no charge at all. But the charge doesn't just keep growing and growing and growing without limit. The charge grows quickly at first, because at the beginning we should expect fast current, because there's no charge getting in the way. Fast current, so fast rate of change. But then as we build up more charge, we get slower current, and therefore slower change in charge. So the change is going to get slower and slower. And when we've got even more charge, we get an even slower current. So the slope of the charge graph is going to get flatter and flatter, eventually leveling off towards an asymptote. If this is approaching an asymptote, would we call that exponential growth or exponential decay?
Growth?
Not if it's approaching an asymptote. And this is often a very common misconception. If the exponential growth does not necessarily mean that the graph is an increasing function. Exponential growth means it keeps changing without any limit. It just goes up, either shoots up towards positive infinity or shoots down towards negative infinity. In this case, though, this is not shooting off towards either infinity. This is approaching an asymptote. So the fact that there is an asymptote that it approaches as time goes on, that's what indicates that this is exponential decay. And I know it's tempting to call this growth because the value is increasing. But what's actually decreasing here is the difference between the value and the asymptote. If you take a look at what's going on at some instant in time, here's the value, here's the asymptote. There's a difference between the value and the asymptote. If you wait a little bit more time, the value has increased. But if you look at the difference between value and asymptote, that difference has decreased. A little bit later, we got the value, we've got the asymptote. The difference just keeps getting smaller and smaller. So that difference is what's decreasing here. We call this exponential decay because the difference between the function and the asymptote is getting smaller and smaller and smaller. And the asymptote is really the most sensible thing to measure everything from here. So I would always try to think of exponential functions as measured from the asymptote. If the function is getting closer and closer to the asymptote, then we would call that exponential decay. If it's getting further and further from the asymptote, then we would call that exponential growth. So for example, if you have a function that looks like this, we would call this exponential growth. Even though it's a decreasing function, if you take a look at the difference between value and asymptote, that difference, and then a little bit later, we've got this much difference. A little bit later, we've got this much difference, and then even more. In that case, the difference between function and asymptote is increasing, and it's going to keep increasing without any limit. It just keeps growing faster and faster. So this would be exponential growth, even though it's a decreasing function. This would be exponential decay, even though it's an increasing function. Any questions on that distinction so far? All right, so if we're talking about exponential decay, how do we reflect that in the exponential function itself? What has to be in the exponential function in order to make it exponential decay?
Negative.
Yeah, we've got to have a negative sign in the exponent itself. So e to the negative t will be exponential decay. However, e to the negative t on its own is going to decay towards what value? What's this going to approach as t gets larger and larger? Like if you've got e to the 1,000 or e to the 1 million, or sorry, e to the negative 1,000, e to the negative 1 million, what's that getting closer to?
Asymptote.
We want it to approach this specific asymptote. But if you look specifically at e to the negative t, what asymptote would that alone approach? If you're making e to the power of more and more negative numbers.
Well, if it's more and more negative, it gets smaller and smaller.
Right. This is going to get smaller and smaller, closer and closer to
0.
Right, 0. So this function alone, if you just have a constant times e to the negative t, that's always going to approach 0 as the asymptote. But we don't want 0 as the asymptote here. We basically want to take a function that approaches 0, take that function and shift it up so it's getting a new asymptote. So how do you shift a function? What do you do to a function to shift the whole thing up on the graph?
Add a constant.
Right. You add a constant, and that constant is just the equilibrium value. Let's say we could call this Q max. So adding Q max shifts the whole thing up. So instead of approaching 0, it's going to approach Q max, the asymptote. That also means that this multiplier here can't just be Q0. Because if we plug in 0 for t, e to the 0 is 1. But we don't want the result to be Q0 plus Q max. We just want the result to be Q0. So this actually needs to be not Q0, but actually the difference. What we need here is Q0 minus Q max. The difference between initial value and maximum value, or asymptote value. That way, when we plug in 0 for t, e to the 0 is 1. So we get Q0 minus Q max times 1 plus Q max. The Q maxes cancel out, we're left with Q0. So this is the format we're going to need for the multiplier if we have some asymptote that's not 0. Of course, if the asymptote is 0, you just plug in 0 for Q max in both cases, and you still get Q naught times e to the negative t. We also need one more modifier here, because e to the negative t assumes a very specific rate of decay, but we want to have other rates of decay possible as well. So how could you modify e to the negative t to change how fast this decays? To make it decay really fast, or make it decay more slowly, or really slowly? What difference in the equation would lead to a difference in how fast the function decays?
A variable before like the t?
Yeah, if we have some multiplier next to the t in the exponent itself, usually written as a times lambda. The value of that multiplier will influence how fast the function decays. Any questions on that so far? And it turns out that for a resistor capacitor circuit, it's the only things in the circuit if you just got a single loop with one resistor, one capacitor, and optionally a battery. Do you remember what that multiplier is? We looked into this a little bit last time when we were when we were solving that exponential decay function with just the resistor and capacitor. Yeah, that turns out to be 1 over RC. So for specifically these example of a circuit with just one resistor and one capacitor, that multiplier is actually going to be 1 over RC. So we really get e to the negative t divided by RC. So that is our exponential decay function for the charge on the capacitor. We've got e to the negative t over RC. So the R and C, the resistance and capacitance, both influence the rate of decay, times this value Q naught minus Q max, which basically just determines where it starts, plus Q max, the asymptote that it approaches, the maximum charge it will approach after a long time. That's enough to guarantee that the function looks exactly like we want it to, the exponential decay. Any questions on that format for the equation so far?
Would you be able to explain again why we need to include the Q max if they cancel out?
In this one here and this one?
Yes.
Yeah, we actually want them to cancel out at time 0. Because if they didn't cancel out, like if we didn't have this Q max here, the idea is we want to make sure that when you plug in 0 for t, you get the starting value, which in this case is 0, but it doesn't have to be 0. If you plug in 0 for t, let's say we just had a Q naught here. If you just had Q naught times e to the negative t over RC plus Q max, and we plug in 0 for t, what's e to the 0?
1.
So that means we would just get Q0 times 1 plus Q max. But we don't want the starting value to be the starting value plus Q max. We want the starting value to be just Q naught. So we need to have this be Q naught minus Q max, so that when we plug in 0 for t, and this just becomes 1, this becomes starting value minus Q max plus Q max, which equals starting value. So we need the minus Q max there to cancel out the plus Q max here at time 0.
Oh, okay. That makes sense. Thank you.
So we want to get Q naught when t is 0. Any other questions on that so far? So we now have a general equation for the charge at any time. And we could even figure out specific values for some of these. For instance, in this case, we know Q naught is 0. In this particular situation, the capacitor starts off uncharged. The capacitor is empty. So we can fill in 0 for Q0. And we know R and C, that's just going to be 3 ohms and 2 farads. Multiply those, 3 ohms times 2 farads, you'd get 6 seconds. Because ohms times farads, the units work out to seconds. So you get e to the negative t over 6 seconds. And I guess all that's left then is Q max. So Q naught is 0. RC is negative 6 seconds, or 6 seconds, the negatives here. We still just need to find Q max. So how do we figure out the maximum charge that this is going to approach as time goes on? If we go back to the loop rule, if we want to know what's the largest charge can possibly be, What should we assume is true about the current if we want charge to be the largest possible?
Is it 0?
Yeah, if the capacitor fills up, we should assume that the current is now 0. Because if the current was not 0, if current was still flowing, that means the capacitor would still be in the process of filling up. It wouldn't be full yet. So to figure out what the maximum charge is, assume that the current has come to a complete stop, because that means the capacitor is full and is not going to get any more charge. You can also see that from the fact that current is the derivative of charge. So if we replace current with Q prime, the derivative of charge, we can use the idea from calculus that you get the maximum or minimum value of a function when its derivative is 0. To optimize a function, to find the max or minimum value, set the derivative equal to 0. In other words, set the current equal to 0. So if we want to find Q max, assume current has come to a stop. And we would call that a steady state. While the current is flowing, this is not a steady state because the capacitor is changing how much charge it has and the current is changing how fast it's going. Everything's changing as time passes. But if you wait long enough for the current to dwindle to 0 and the charge to reach Q max, then from that point onwards, nothing's changing. It has reached a steady state. So if we actually plug those in, we get 12 equals 0 plus Q max over 2. 0 times 3 is nothing. How else do we solve for Q max?
$24.
Yeah, multiply by 2, you get 24. And since that's volts times farads, that ends up just being coulombs because farads is coulombs per volt. Farads is coulombs per volt. Volts cancel out, we get just coulombs. So that is the maximum charge here. We can now fill that in for Q max. And we can say Q of t equals 0 minus 24 is just negative 24. So we're left with 24 coulombs minus 24 coulombs times the exponential function. So there's our actual exponential decay function. This is our exact function for the charge in the capacitor at any time in this circuit. And note that if you plug in 0 for t, you get e to the 0 is 1. So you just get 24 minus 24, which is 0. So this correctly predicts that at time 0, you start with no charge. Whereas if you plug in a very, very large number for t, like let's say t is 6 million, e to the negative 6 million over 6 would be e to the negative a million, which is basically 0. So this whole term drops out and you get charge after a million seconds is 24 coulombs. So this correctly predicts a function that starts at 0 and asymptotically approaches 24. Any questions on that so far? And we could do the same thing with current. We could say current is also going to be an exponential function. If we want to write out a function for current, we could use exactly the same approach, just with some slight differences. We could say current is going to follow this exact same pattern. Initial current minus asymptote current times e to the negative t over, and the current's also going to follow the same time constant. It's still going to have negative t over RC. Ultimately, everything in this circuit that decays together is going to decay with the same rate. So both the current and the charge are both going to have the RC as the time constant. And then plus the asymptote current. However, for the current, we're assuming that after a long time, the current approaches what value?
0.
Yeah. After a long time, current is 0. That means we can assume that current asymptote is 0. The asymptote is going to be 0, asymptote is going to be 0. So in this case, we get a rather simpler function. It's just I naught times e to the negative t over RC. If we can figure out what I naught is, then we're good. So how do we figure out what the current is at the very beginning? Like the instant we flip the switch, how do we figure out what the current is? Yeah, we can set the charge equal to 0 because we know that at the very beginning, the instant we flip the switch, we were assuming the capacitor started off empty. So you can plug in 0 for charge. Or if the capacitor did not start off empty, you just plug in whatever starting value for charge you have for Q. But since the capacitor starts off empty, we can say at time 0, the capacitor is empty. Charge equals 0. So we get 12 volts equals current times 3 plus 0. The loop rule becomes much simpler by just plugging in 0 for Q. And then how would you solve that for current? If current times 3 equals 12, then what does the current have to be? Yeah, divide by 3, you get current equals 4 amps. And that'll be I0, the starting current. So to figure out what's going on at the beginning, plug in the starting charge and solve for the current. To figure out what's going on after a long time, you can assume the current dwindles down to 0 and then solve for the charge at the very end. And this is often a very useful way of approaching any exponential decay situation. No matter whether it's electrical current in a circuit with a capacitor, or fluid flowing out of a tank, or heat flowing from one place to another, or a cup of coffee cooling down, as long as you can be reasonably confident that it's exponential decay, it's a good idea to start by finding what's going on at time 0 and what's going on after a long time, in this case, Q max. If you can figure out what's going on at time 0, that's your starting value. If you can figure out what's going on after a long time, that's your asymptote. And that's most of what you need to know for an exponential decay function anyway. All that's really left beyond that is the rate of change. In this case, we know that's RC. So let's fill that in. For the current, we get current at any time equals I naught, which we found to be 4 amps, times e to the negative t over RC. And we know RC is 6 seconds from multiplying resistance times capacitance. And then plus I asymptote, but we know the asymptote it's approaching is 0. So there's our formula for current at any time. If you want to know what's the current after 17 seconds, you can just plug in 17 seconds for t, multiply that out, and you get the current at that time. Any questions on that so far? And we could graph both of these. We could graph, if we wanted to graph charge and current. Let's see what those would actually look like. If we make a graph of charge versus time and a graph of current versus time. And we know the important values are going to be 24 coulombs for charge. That's Q max. And also, we know 4 amps is going to be important. That's the starting current. So we know current is going to start at 4 amps, and it should decay towards 0. And we know charge is going to start at 0 and decay upwards towards an asymptote of 24. So just based on those concepts, just the starting value and asymptote that it's approaching for each one, we have an idea of what these functions should look like. But we want to be more precise than that. We want to be able to get a more accurate depiction of how fast they're decaying towards the asymptote. So what idea could we use to describe how much time it takes for them to decay a certain amount?
Slope.
What was that?
Oh, the slope of the either graph.
Yeah, the slope, but the thing is the slope is changing. Since it's not a straight line, the slope is changing. So we want to use, the time constant or the half-life. The time constant and the half-life are both just descriptions of how much time it takes to decay a certain amount. And that is certainly related to slope. It's just that the slope is changing from point to point, whereas the time constant or half-life is a more stable, reliable, it's the same time constant the whole time, or the same half-life the whole time. So it's a way of describing how much time it takes to decay a certain predictable percentage. So the time constant, for instance, in either of these equations, what quantity is the time constant that we're talking about?
Is it negative 2 over RS?
Yeah, or specifically just the RC. The time constant here is RC. Usually written as tau. So in any circuit where you just got one resistor and one capacitor and optionally a battery, the time constant is always going to be the R times C. More generally, the time constant is whatever time you can plug in for t that makes the exponent -1. Because if you plug in, like here, we've got this t divided by 6 seconds. If you actually plug in 6 seconds for t, you get -6 seconds over 6 seconds. That just becomes -1. So time constant is the amount of time you have to plug in, so the exponent becomes -1, which means you get 1 over e of the original amount, or 1 over e of the original amount. And since we know the time constant, 6 seconds, we can actually mark that on the graph and get a much more accurate depiction of how fast this is decaying. So if we actually mark 6 seconds on the graph, and let's try some multiples of that. So maybe 6 seconds, 12 seconds, 18 seconds. Or we might even just label those as multiples of the half-life. We could call this tau. We could call this 2 tau. We could call this 3 tau as just labels for time. So we're basically parceling out amounts of time based on the time constant. And each time one time constant passes, we should expect the original amount to decay to e to the -1, that is 1 over e of what it was. So after one time constant, 1 tau, amount left is 1 over e, because that's e to the -1 of the original amount. And 1 over e works out to about 0.37, so we could call this about 37% of the original amount. So after 6 seconds, we should be left with 37% of the original current. Or more precisely, 1 over e of the original current. So we take 4 amps and divide that by e. And that'll tell us how much current is still flowing after 6 seconds. So 4 divided by e is about 1.47. So after 6 seconds, one time constant, we should expect about 1.47 to be remaining. Mark some more points here. So 1.47 is going to be a little less than 1.5, somewhere around there. So that can be used as another data point on the graph to get more accuracy. And then 6 seconds after that, how would we calculate how much is left 6 seconds later?
Isn't it 1.4 times the person, because every time it's 37% less. So if you multiply by 37%.
Mm-hmm. Yeah, we could just take that value and multiply by 37%, 0.37 again. Or more accurately, divide by E again. So you could take 4 amps divided by E, or multiplied by about 0.37, and then divide by E again. Or if you're dividing by E twice, if you're taking 4 divided by E and then dividing by E again, you're really just taking 4 and dividing by what? If you're dividing by E twice, what would we call that?
E to the 2?
Yeah, so we could just find this value by taking the original amount. We don't even need to refer to our rounded off value at all. We could just take the exact original amount, 4 amps, and divide by E squared. So 4 divided by E squared is about 0.54. So after 12 seconds, we'll have about 0.54 left, a little more than half an amp. And then after 18 seconds, that's 3 half-lives. So we can just take original amount divided by E to the 3rd power, or this value divided by E again. But I find it's generally much more accurate to refer back to the original value whenever you can. And 4 divided by E cubed is about 0.2. That'll be something like this. And you could keep this going for more and more time constants. But this looks like it's enough information to sketch in a pretty good curve. Something like that. So by plotting more and more data points, you get a more and more accurate depiction of what this exponential decay graph looks like in terms of how fast it's actually decaying. You could also do this in terms of half-life. If you calculate the half-life, you can go that far forward in time and the amount drops by exactly half. That much forward in time again, and that amount drops by exactly half to half of what it was. Another half-life, exactly half of what it was, and so on. And if you know the time constant, do you know how you would calculate the half-life?
Yeah.
How would you do that? If you know the time constant is 6 seconds. What exactly is half-life? It's the amount of time it takes for what to happen?
I0 to be half.
Yeah. We want to get to half the original amount. So if we try calculating that, if we just say, assume that current at some time, let's say capital T, is half of the original amount. If we actually just set this formula equal to half the original amount equals I naught times e to the negative t over RC. Let's say capital T. So capital T represents that specific amount of time. How would you start solving that for capital T here? What can we get rid of right away?
I0.
Yeah, divide both sides by I0, and those just cancel out. Which is good because the time constant, or the half-life, shouldn't depend on how much we start with. It should just depend on the rate of change, the R and C. So 1/2 equals e to the negative t over RC. And to simplify things a little bit here, since we've got a fraction and a negative exponent, I'm going to raise both sides to the -1 power. So we get 2 equals, and then here the negatives cancel out. We just get e to the t over RC. And then how would you get that t out of the exponent?
Take the natural log.
Yeah, if you take the natural log of both sides, left side we get natural log of 2, right side logarithm and exponential cancel out, so we just get t over RC. That is t over the time constant. multiply both sides by RC, and we get the half-life, often written as capital T sub 1/2, equals RC times logarithm of 2. That is the time constant multiplied by logarithm of 2 equals the half-life. So since we know the time constant, 6 seconds, we can calculate the half-life just by multiplying that by a logarithm of 2. 6 times natural logarithm of 2 is about 4.16 seconds. So you could plot more data points on this graph as well. If you mark 4.16 seconds, that's the half-life, you should expect exactly half of the original amount left. It drops from 4 to 2. One half-life later, if you go from 4.16 to double that, 8.32, that's 2 half-lives, so we should expect half of the original amount. So that's going to be 1. And so you can use this idea of half-life as a way to get even more data points on the graph. You can mark off time in terms of half-lives, multiples of the half-life, or in terms of multiples of the time constant, or both. If you mark off both the time constants and half-lives, you can get lots of data points on the graph and get a very, very accurate smooth curve connecting them. Any questions on that so far? So let's try graphing charge as well. And for charge, I'm just going to mark it off in terms of half-lives to make the calculations easier, because it's easier to just take half of something than to try to find 37% of it. So we'll mark 4.16. That's 1 half-life. And then 8.32, that's 2 half-lives. And then I guess that'd be 12.48. And then one more would put us at 16.64. And we could keep going, but I think 4 half-lives should be plenty. We know that we start with 0 charge. 1 half-life later, we're not taking half of 0, because that would just still be 0. But what should we measure everything from?
Qmax.
From, sorry, what was that?
Qmax.
Yeah, from Qmax. The asymptote is an excellent place to measure everything from for any exponential function. So instead of thinking of the starting value as 0, I would think of the starting value as 24 below the asymptote. We start 24 below the asymptote. After 1 half-life, we take half of that difference. So what's half of 24 below the asymptote?
12.
Right. So it'll be 12 below the asymptote. And 12 below the asymptote is going to be 12 coulombs. So 1 half-life later, what's decaying is the distance to the asymptote. That distance is going to decay to half what it was. So at 1 half-life, 4.16 seconds, will be at 12 coulombs. 1 half-life later, that distance, that difference between value and asymptote decays halfway again. Right now, for instance, we're 12 below the asymptote. 1 half-life later, what's half of 12 below the asymptote?
18.
Yeah, because that'll be only 6 spots below the asymptote. So halfway of that, we're only 6 below the asymptote. So that will be at 18 coulombs. We're not taking half the value, we're going halfway towards the asymptote. And then half of 6 would be 3, so we would end up 3 below the asymptote. Which would be what actual value?
21.
Yeah. So at 12.48 seconds, we should expect 21 as the charge. And then another half-life goes by, we take half of 3 below, we get 1.5 below. So that'd be at 22.5. And so this half-life approach also gives us plenty of data points to work with. And we can now connect those with a smooth curve, Or alternatively, you could also fill in the time constants if you want even more data points to work with. But the half-life points give us enough information to get a very good idea of how quickly that's decaying towards the asymptote. You can also get all these data points by just plugging in values to the equation here. For instance, if you actually type in this into a calculator using, let's say, 12.48 for time. So if I just type 24 minus 24 times e to the negative, let's say 12.48, divided by 6 seconds, then according to this, I'm getting, I don't know if this will show up, 21.001. So I've rounded off the time, the half-life a little bit, so it's not absolutely exact, but within 3 decimal places, the 21 value we get just from using the idea of half-life is very, very accurate. So the half-life is a very useful tool of graphing all these data points and getting a very good curve without even needing the equation at all. We didn't actually need this equation to draw this graph. All we needed to know is what value it starts at, what asymptote it's approaching, and the time constant or half-life to get an idea of how quickly it's decaying towards it. So those 3 pieces of information alone, where it starts, what asymptote it approaches, and either the time constant or the half-life, that's enough information to draw a very accurate exponential decay graph and at least predict or estimate what it's going to be at any time you want. So this is a very useful approach to any exponential decay situation. Any questions on that? All right, sounds good. We can take a look at some more examples next time. Have a good weekend, and I will see you then.